Okay, so now I want to talk about essential fatty acids and the eicosanoids, which are related. The reason fatty acids are essential and that they're nutrients that you have to have. You can't go on a totally fat-free diet because you won't be able to produce any eicosanoids, which are very important hormones, and they regulate a lot of processes, inflammation and pain and you know, all sorts of things like that. So these are, in particular, we can think of something called C18 polyunsaturated fatty acid, and most common one would be linoleic acid, C19, C18 912, and C18 912 15, every third one, right? And this is, okay, so I can draw it like this. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9. And okay, yeah, one more out of there. Okay, and so you can see this is a 9 and the 12, and this is a 15 position. These are also called, this is an omega-3 because we have the 1, 2, first bond from the last end. Omega is the last letter of the Greek alphabet, so 3 from the end is an omega-3, and 1, 2, 3, 4, 5, 6 from the end is an omega-6 fatty acid. Okay? Now, remember, as we called when we made unsaturated fatty acids, we can only produce unsaturations in this region, okay? From 9 back to 5. Okay? Whereas plants and lower animals, invertebrates mostly, crustaceans and things like that, can produce them in this whole region all the way up to 15. I'm going to call this mostly plants. And this is higher vertebrates. Okay, now this is most important because what we have is an important fatty acid here. There's two of them really I want to talk about. Remember I told you you had to learn this one, C24, 5, 8, 11, 14. Okay, this one. Okay, and then this turns out to be an omega-6 fatty acid because this is 14, 15, 16, 17, 18, 19, 20. See, omega-6. There's another one, so this is called arachidonic acid. There's another one called EPA, right? Icosapentaene ioic acid. Okay, it looks just the same, except it's C25, 5, 8, 11, 14, and 17. Okay? And it's the omega-3. Okay, there we go. So these are going to be, in particular, arachidonic acid is kind of the most common one. So we have to learn about eicosanoids to understand the difference between these EPA. Icosapentaene oleic acid. So icosa means 20, pentaene oleic acid. Okay. So I'm going to show you the mechanism. We didn't talk about eicosanoids in the first unit on what things were because it was really kind of complicated to really even remember what they are. Okay, so I'm going to actually show you how they're made, and then it's just like in steroids. You can remember what they are by knowing how they are made. Okay, so we're going to take arachidonic acid, and I'm going to draw it in this form. And it's a very symmetrical form here. Okay. This is a very important enzyme that does this. Is called cyclooxygenase. Okay. Okay, and so this is going to be called the Cox mechanism. COX mechanism. And I don't know if you guys remember, a couple of years ago, there was a big thing where they produced Vioxx and Celebrex as these new anti-inflammatories. You know, one of the major diseases, major drug targets is inflammatory diseases, for in particular arthritis and certain other conditions. People take them a lot, and they're painkillers, right? Because when you get inflammation, you get pain. And so Merck in particular produced a COX-2 inhibitor, and it turned out that it had severe side effects and killed some people, and they knew about this in the trial, and they got into a lot of trouble because they had to pull it off the market after it was approved, and they had some data to indicate that it caused excess heart attacks. And they didn't reveal that to the FDA at the time. And they got in a lot of trouble, and nobody actually went to jail, although it's arguable that they should have. Got one more. There we go. Omega-6. Okay? So, the way this works, okay, this goes through a kind of radical mechanism. And what we're going to do, this is a cyclooxygenase. Okay, so we have this other, in the steroid biosynthesis pathway, we're going to have this other oxygenase mechanism here. And what we're going to do is we're going to first create a radical right here. The first step is we take this tyrosine radical, and we're going to leave aside how this tyrosine radical is produced. And what it's going to do is it's going to abstract a proton, which I don't have my pencil. Different color because I don't seem to have my pencil here. Okay, well, never mind then. It's going to abstract a proton from right here in radical form, and we're going to generate a radical on this position here. Okay, so the first step is to do this. Now, and this happens just kind of like this. And then we show this one arrow just staying there. Okay, so one of the electrons comes out of this bond, and it gets taken in this radical, and this radical goes to just a tyrosine. Okay, and that's on the enzyme. And then what happens is, this is sort of a stable radical. This looks like an allene radical. As a matter of fact, this is a bis-allene radical. So it's a very stable radical because you can see the allene right here, and you can see an allene right here. Okay, so it's even more stable than the regular allene. It's completely resonance delocalized over this region. We've kind of bridged the conjugation here by producing only two things. Well, there's only three things. There's only that one remaining hydrogen on this position here, right? So this makes this radical exist in a p orbital now, and it can hybridize with these other ones, and that's really what's happening in the allyl radical. Okay? But because we have a radical, we can now do an oxygen reaction. Okay, so we have oxygen here, and I'm going to draw oxygen in this form. All right, our more sophisticated form. And what we do is we're going to take it like this, and we do a bunch of these radical reactions. Okay, we pull one of the radicals out of oxygen, and the other one comes up here. Okay, and so what do we get now? Well, nothing happened up here. That's still the way it is. But now what we have is we have our radicals move to the end of the oxygen. Okay, and oh no, sorry, there we go. We created this double bond here. And two things. Note that we've kind of created a conjugated system here, and we move this radical over. Okay? So now what we can do is this radical can come and attack this double bond here. Okay? Taking one of its electrons to form a bond. This guy can come over here and take one of these electrons. This guy can come over here, and this guy can come over here. And this guy can come onto another second oxygen atom, molecule, okay, and generate the radical right here. Okay, so in this step here, what do we have? Okay, and the rest of the molecule is still the same. We still have this up here, and we still have 6 atoms here. Okay, omega-6. So the next step, what does it look like? Well, this atom folded up like this. There, and the oxygen is kind of underneath like that. Okay, we formed a bond between these atoms right there. Now this is still the same, 2 bonds, cis, and my fatty acid in the back. And what this has done is this has come up now. Okay, this double bond has moved sideways here. Then we've come here. Now we have a peroxide. radical and 6 atoms. Okay? Then what happens is this tyrosine that's been sitting around here all the way long we could just retransfer the radical here. So I'm going to go like this. And one of them is going to sit on there. And we generate the final product, which is this compound. Okay. And sometimes, so that's a 3-dimensional representation. It's a bicyclic structure. We have a 5-membered ring, and underneath we have this double bond, this sort of peroxide bridging 2 of the atoms in that. Sometimes this is written, I'm going to draw another representation here. Okay. Sometimes this is drawn like this in a kind of a distorted fashion, right, where we draw these oxygens inside. Then we have a trans bond, and then we have OH there. And this is sort of just a top view, a more schematic view. Okay. So this is called prostaglandin G2. Okay. We'll talk more about that nomenclature in a minute. And this is the cyclooxygenase mechanism. You can see in the last step here we've regenerated this radical right there. So it's catalytic. Okay. We have generation of a radical. Radical attacks the first oxygen, creates this peroxide radical. Then this initiates a chain reaction to go all the way through the system. We've created a conjugated system to go. And this little thing through space conjugation is kind of reminiscent of that squalene mechanism, right? Or not squalene, the inositol synthetase mechanism. And in the end, we generate another radical on the oxygen, and then it regenerates the catalytic radical on the enzyme. Okay. So once this mechanism is very logical, right? When you just all you got to do is remember to draw it this way, and then you follow this procedure 1, 2, and you inevitably end up with prostaglandin G2. Okay, so there's a number of prostaglandins, and just so we can go through what they are. This is like learning the prostaglandins. Okay. Okay, so we have this one is sort of the base of it, and okay. So this is G2. This is a G-type prostaglandin. Then we can go to an H-type prostaglandin. This peroxide is very unstable, and this hydrolyzes immediately. And the G-types are never released. We just have that alcohol here. Okay, and this is going to be the same. Okay, and this would be called H. Okay, H-type prostaglandins. Okay. And then the rest of the prostaglandins, well, we're going to break this epoxide and we can get F-type prostaglandins. We're kind of going in reverse. Okay, the nomenclature goes in reverse. I think they discovered these breakdown products, or not necessarily breakdown products, processing products. They discovered these processed products first, and then they had to work backwards and found earlier and earlier. These products are less stable. They don't last as long, although they are released and they have certain initial release from tissues. Okay, and this is all the same. Okay, so this is an F, and then we can go to the E types. We form this. This is an E type. And then we can go to these types down here, which are the C type, where we can dehydrate down here and create a dehydrate and create a conjugated system. And we can dehydrate in the other direction, which is this type. And then we can create this type, regenerate the conjugated system. And everything else is the same here. Okay, and so this is the A, the C, and the B type, I think, and we can create other types all the way through here. The one other most important type is the so-called I type. The I type is this type, where we're going to take this bond, which was, okay, take this thing, and we're going to process it into prostaglandin type I, which has this bicyclic ring structure. Okay, kind of joins right in here. Okay, and then the rest of the molecule. Oh, 1, 2, 3, 4, 6. Okay, and this is so important. This is also called, it has two names. It's either PGI, this would be PGI, or it would be prostacyclin. Cyclin. Okay, that's prostacyclin. This is the thing that got them in trouble with the Cox and with Vioxx and Celebrex. They were trying to attenuate these things that mediate pain and inflammation, and they ended up attenuating prostacyclin, and this caused cardiac problems, and people had heart attacks. We have the D type. What else do we need? Here's the D type. Okay, and we have K, and we have, this is K. And there's J types. There's J. Okay. And they're processed like this. And this is kind of like your map of the steroids. Okay. This is a map of the prostaglandins. So what do you need to know? You need to know, you need to know this one and this one and this one and prostacyclin for sure. And then all the rest of them if you really want to learn it. Now, the unsaturated, let's do one more first. Okay, so this is prostaglandins. The other major type of eicosanoids are, so these are the PGs. Okay, the other major class of the eicosanoids are the leukotrienes, okay, the LTs. Okay, leukotrienes. Okay. Now, it's a little unusual, we call these things trienes, and this is going to be your first clue to what's happening here, okay? They're not really trienes, they're tetrienes, okay? They're going to have 4 double bonds, okay? But they don't have to, and that's going to be when we get to we got to get them all out here first. So in this case, we're going to draw them, and I'm going to draw them like this first. Okay, and this one we draw in a linear fashion to understand what's happening. There. Okay. 6 atoms at the end. 1, 2, 3, 4, 5, 6. Good. So this is C25. This is the right one. So the first thing that happens here is we get some kind of radical mechanism. Same idea. I'm not going to give you that mechanism, but you can kind of think of it as like this. There's kind of like a proton on here. We're going to pull off that proton. This is going to collapse, and it's going to go on to oxygen. And it goes through a radical mechanism, not like I've shown you. That's why I haven't put the arrows in red. You can kind of remember it this way, and what we're going to get is this compound. Okay, we get a peroxide. And the rest of the molecule is the same. As a matter of fact, I'm just going to come up here and I'll draw the rest of, at least the double bonds. Okay, and that is very much like this H, like this G type here, with this peroxide on it. Okay. That's the initial product. And this is not even a leukotriene. This is called HPETE, hydroperoxy icosa tetraenoic acid. Okay, tetraene because it has 4 enes, hydroperoxy because it has this. Okay, hydroperoxy icosa means 20, tetraenoic acid. Okay. And then the first leukotriene happens like this. What we can do is we can collapse this thing, and what we're going to do is we're going to pull off a proton right here. Okay? So we have a proton on here. And some base is going to pull that off. And then we're going to collapse this like this, and this like this. And then this guy's going to come up here, and we're going to kick that off here. Okay? So what did we get? This is not going to be a mechanism you need to know, but it's really almost impossible to understand, to get what the first leukotriene is without thinking of this mechanism. I know I couldn't do it. So we're going to produce, okay, so here's this system here. This is the last 2 double bonds here. 5, 8. This is the 11 and the 14 double bond. Then we collapse this and we produced a double bond here. And then this used to be a double bond. It's now a single bond. And then there's a double bond. Okay? And then there's a single bond where this double bond used to be. And we have this epoxide. Okay? There you go. So this is LTA4. Okay? Yeah, LTA4. Okay? Has this thing, the first leukotriene. Now, what we can do is we can resolve this epoxide. Remember we saw an epoxide in various mechanisms before. We had squalene epoxide, for instance, and that we said that epoxide was very unstable and it helped drive the formation of linosterol. Well, we do the same thing here. We can have two ways to do this. The first way, we're going to produce leukotriene B. Okay? And what's going to happen is a water molecule, really a hydroxide, can come down here and it can attack here. And we can go through this. See, we started off with a fatty acid that's not conjugated, kind of stable. Like we say, most fatty acids are not conjugated in their base form. And we're creating reactivity when we make them conjugated. By oxidizing this to the peroxide, we shove this double bond forward and allowed this conjugated system to form the first leukotriene. Now the next see, now we have 3 bonds conjugated, and we're going to use reactivity through this conjugated system like this. There. And that's going to produce right here. Nothing happened to that last one, but this next one got an oxygen on it, all right? Kicked it down, and then we have trans, cis, oxygen. There we go. And I guess I got to put 6 bonds to the end, and this would be LTB4. Okay? We can also just break this. We're going to break this with this compound. I'm going to draw it out. Why not? It's a good exercise for you people. So who knows what this is? You should recognize this right now. Okay? Almost. It should look a little unusual to you. This is something called glutathione. And it's a peptide bond between glycine, cysteine, and glutamic acid. Okay? And so what's going to happen here is this sulfur nucleophile is going to attack and just bust the epoxide. And that's going to create LTC. Okay, everything stays the same here. Okay. And then this gets further processed to LTD, LTE, and various other leukotrienes. Okay, down. So coming back, so this was all done on. Look, these are the 2 main classes. We have we have several leukotrienes, and we have a whole bunch of prostaglandins, and we have these essential fatty acids, and we've made them all from arachidonic acid, which is the way they were figured out. All of these things can happen, though. These things can happen with only the double bonds, not that last double bond. See, here's the essential double bond. The essential double bond is this one. Okay, the one that we can't make. We can't make any of these. Okay, we can't make the omega-3 and the omega-6 double bond. Well, if you look at these guys, here's the omega-6. Okay, so we can't make any prostaglandins without omega-6s. Okay, we can't make them. We can make we can make leukotrienes without this one. Okay, so we can make leukotrienes, and this is something they were discovered with no essential fatty acid. If you don't have them, you get leukotrienes, except the way they're numbered. Okay, so these are numbered. Remember I said the first one, LTA4, LTB4, LTC4. This refers to how many double bonds are in the molecule. With no essential fatty acids, we would take, all we could produce is C2258. That's what we can do without those unsaturations down the way. Those 5811. Okay, because we can put it in that 9 position, and then we can extend it 1 position into 11. Okay, so we can't produce the omega-6 position. Okay, that would produce LTA3. right, which would just be this compound. It would be an omega-9 there, just by example. And I have to make 9 acids at the end here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. LTA3. This is inactive. Okay? And all the rest of them, I can make LTC4, LTE4. Okay? I can make the leukotrienes with 3. So this is what we can do. If we make an omega-3 fatty acid, I can make LTA5. Okay, and LTA5 would look, well, you can just draw LTA5. There's your epoxide, and they all have these homologs here. So then a cis one, and then another cis one, a trans one, and then another trans, and then we have to have a cis one, and another cis one, and then another cis one. There. And this shouldn't be there. Okay, LTA5. Same thing, we can produce the 5 series. And in prostaglandins, these things, this is PGG2, okay, and this is going to be PGH2 and F2 and everything like that. These are made from the omega-6s. The omega-3s produce H3, and all they produce the 3 series prostaglandins, okay? And so each prostaglandin, and it's not fully understood right now, and that's why there's varying evidence about, so these produce the 2 series and these produce the 3 series. Okay? If you eat more omega-3s, you get a different profile of prostaglandins and a different profile of leukotrienes, and they have different effects. And it's a little controversial. I don't think it's not fully understood yet, because some of them, like for instance, like the F ones might be